I don't know how. I have also a copy of this CD. Yeah? So, and you will see how this look like by now. We will go through this CD till we are going to the field. And the thing is, it is actually forbidden to make copies out of it and handing it out. Yeah. So, but the CD is actually very helpful. You will see this now, and it is also running on a PC. So, and maybe I will give this copy to Neil, which I have, and then you can just arrange it with him. Yeah? But officially, I should not know it that you have it. Or we can install it in the computer lab, on these computers in the geography lab, and then you can go there. But it's not always open. Or we can install it on this PC here, and then you can always come when you have time and playing around. Or we are doing all the options. So that is called this mineralogy tutorials, and that is belongs to this book from Cornelius Klein. So, and the book itself is also in the library, and I have also a copy of this book. But actually, you don't need the book. I mean, you're just going through this CD. Yeah. So, and then I have here the continue button, and I should just have something like a pad. Yep. So, we have here 4 topics. Module 1 is crystal and mineral chemistry. So this topic we will go a little bit faster through, because there is a lot of overlap from the things what we have done by now, but it doesn't matter if it's not a harm if you're hearing it, some things again. Then we have the crystal. Module 2 is the crystallography. Module 3 is crystallography, internal order and structure. And module number 4, that is the systematic mineralogy. So, and here we have then some pictures and some movies, yeah? And maybe we can just put the thing here more far away, then it is also bigger. So, and then I go here more to this side. So, and here you have then you have different buttons. Here the coordination of the ions. I will now not go through it because we have done it by now, but we have here the coordination number, And the coordination number can range between 3, 4, 6, 8, 2, and 12. So, and now we will check how this looks like then. So, and here we have the size, how it is correlated with the size of the atoms, and then the radius ratios. So, but anyway, here we have a linear, oh no. That is now not good. Just close the curtains. You know, one cannot see it very clear on the board, yeah? One can only see it if one knows it, how it should look like. Or can one make it more bright?
Because I have to change something here.
No, here I can nothing change. That is just a bad beamer. Yes, that is full power here. Do we have also another one somewhere?
One I think is in lower campus. From 11 to 12.
Yes.
So I have to check in lower campus. I have to check in lower campus.
Yes. So, but if we are starting the movie, maybe one can see now something. Yeah, that's not good. It is not good. So we are going here from a linear coordination in a trigonal triangular coordination, then in a octaedral coordination, in a tetrahedral, cubic, and finally in the closest cube octaedral coordination, which is then the closest package, yes, which I showed you as well. So here we have, yeah, that's not good. So, but anyway, here we have again the linear coordination, and the linear coordination means here one can see it better. One have here only two atoms. These are probably oxygen, and here in the middle you have a smaller matter. if we are going to a triangular coordination, then we have just the arrangement of 3 bubbles. If we are going to tetrahedral, then we have just a coordination of 4, and that means 1, 2, 3, 4. So, and that means you have then a coordination number of 4. So that means in the tetrahedral coordination with the cation surrounded by 4 anions, yeah, and the anions are usually the no oxygen. So then we have the octahedral coordination, and you know by now what the octahedron is, yeah. We have then the coordination number of 6, yeah, because you have here 1, 2, 3, 4, 5, 6 anions. Then we have the cubic one, and the cubic one has then a coordination number of 8. So, and that is then here just 1, 2, 3, 4, 5, 6, 7, 8. So, and that is then just the radius between your cation and the anion, yeah? So, and that is then in this case varies between 0.732 and 1. So, and that was written in the other ones before as well. So, and now we have the closest bagging. So, in the closest bagging, I showed you, or I told you about this example that we are putting was squeezing our atoms in the closest bagging package, and there we have a coordination number of 12. Yeah. So, and there we have then the central cation is surrounded by 12 anions. So in this diagram, yes, in this diagram one can see them now better. In this diagram we have the relation how the coordination number is reflected by different cations. In the middle we have here magnesium, iron and calcium. So, and here we have the radius of the radius of our cations. So, and then how is it related with the coordination number? So, if we have the closest baggage, then we have, it's also depending then on the different cations in the middle, and the closest baggage we can produce the knot with elements like magnesium and iron, so, but we can produce it with elements like calcium, and that is all. It depends then always on the size of the bubbles. Yeah. So when you the thing is working just with cations and anions or bubbles, as I am saying, that is one of the smallest elements what we have here on life. Of course, there are also some smaller ones, but then you are going in nuclear physics, and that we are not doing. We are just working here with these elements which you can find in the periodic table, and with these elements you can build up everything what you find on this planet, also all the plants and everything. So, and we are dealing here with rocks and minerals, and that means that it's just anorganic stuff. So, and this shows you what our why we are doing this. That is just how our minerals are changing by changing pressure and temperature and other chemical conditions. Yeah. So, and if you are going now back, then you can just go to previous year. Then you have here just again the description. So, and then we can go just again here, that's always a little bit forward and backward. Here the closest packing again. So that is if the radius from the cations and the anions is 1, yeah, and we have a coordination number of 12. So, and there are two different stacking schemes. Yes, you can see this then in the movies, if one can see them. So here yes, now one can see it better. Here we have now this arrangement that we have, in the central we have one dark blue atom in the closest packing layer. So and now here is again the movie. So that is this atom in the middle. So and if you are making then this closest packing layer, then this atom in the middle is surrounded then always by 12. So and now you are putting the next layer on the top. And then you have your closest packing layer, yeah? Here in the middle you can see already the blue atom, and that is then surrounded by the 12 onions. So and now we have this for the hexagonal system. Now, I mean, I told you before we have at first a hexagonal system, and then we are making then a cubic system out of it, and that is shown now. So here we have now our hexagonal thing. You can see the shape here, yeah? So and then you are putting just different layer on top here, and then you have the closest package in the hexagonal system. You are stacking them then together. So and that is the way how it looks like in such a stacking model. Yeah, we can use just a bubble model, or we can use a stick and stacking model. And here you have your hexagonal shape. Yeah. So now we are going into the cubic system. So we are starting again with the hexagonal system. So and therefore we have now, we are producing now layers of A, B, C, A, B, C. So and now you have here the surrounding thing is still hexagonal, but here inside you have this cubic thing. Can you see this? So and that, but I showed you this also in class by using the PDFs. So and that is then this is a pressure dependent thing, yeah, because you are looking for, or because your minerals are looking for, to reduce the volume for a given mass, yeah? So, and then you are just changing the crystallographic system, and that is one thing, and I show this to you by using this polymorph or variations from the mineral parts, yeah? You have there a lot of things inside, yeah? So, and that is now how it looks like. That is now the closest packing. And there you have also this closest packing is then made while you are going from the hexagonal into the cubic crystallographic symmetry. So illustration of crystal structures. So yeah, that is just that we can choose, or we have the different models. We have the closed packaged models, then we have the open ball and stick models, and the polyhedra models. So in polyhedra models you have seen by now a lot. So here, for example, we have the ball model, yeah? So here we have an halide, and an halide, you know what an halide is? That is salt, yeah, NaCl. So and the halide is cubic. One can see it just from outside. Now we can just check how it looks like. So here we have this halide. Now in a bigger scenario, or in a bigger picture. So, and here the sodium is here in red bubbles, and the chlorine is here in white bubbles. So, and now we are making from our bubble model a ball and stick model, yeah? So, and that means you are connecting then just all the things, all the bubbles here with sticks. So that is the ball and stick model. So, and now close pack to a ball and stick. That was this. Then we are going here ball and stick to polyhedral. So, and now that is the ball and stick. And now we are going to the polyhedral, and that you know by now, these are our polyhedrals, yeah? You have them, these polyhedrals, now in a lot of different pictures on your PowerPoint, yeah? On your PDFs. So, and these are the three models to describe or to build up minerals, yeah? So, and one is using such models because we cannot see the bubbles, yeah? So, because they are too small. I mean, you can see them under an electron microscope with a very high resolution. And if you are choosing a resolution of a magnification of 200,000, then you can see the shadows, and they are smearing around, yeah? And I saw them one time in Germany, and that was in Freiburg, I think so. And one can only use then this electron microscope during night. That is because of the traffic. Because if a big truck is just running close by, then the whole picture starts to move. So it is a very sensitive thing. So now we have the thing for the fluoride. So again, a fluoride is a calcium fluoride. So, and the calcium bubbles are here in green, yeah, but here is one, this is just the ones which are sitting inside, and the fluorine is white. So then we are making just the ball and stick model, yes, such an fluoride is also cubic. So, and now we can go from ball and stick to polyhedral. So then you are forming your tetrahedrons and your octahedrons, yeah? Yes, here is one sitting, and here is one sitting. And finally the quartz, because we talked a lot about, or I showed you a lot of figures from quartz. So this is the arrangement of the tetrahedrons in the quartz, yeah? So here we have our tetrahedrons, and around the tetrahedrons on the corners, there we have our oxygens. So now we have here our ball and stick model. Here we have then from the ball and stick to the tetrahedrons. Yes, and of course in the quartz you can only see tetrahedrons because the quartz consists only of tetrahedrons. Yeah, you know this by now as well. So then we have Pauling's rule, that is something new. So rule number one, a coordination of a polyhedron and of anions is formed about each cation. Yes, you know this by now also. You have in the middle, you have your cation, and then this cation is surrounded by the anions. The cation-anion distance being determined by the radius sum and the coordination number, as you know by now as well, of the cations by this ratio, and that is the ratio of your cation divided by the anion. This is illustrated in the graphic. Rule number 2, we have the electrostatic valency principle that you know also by now, that is controlled by the electrons in the outermost rim. In a stable structure, the total strength of valency bonds that each an anion from all the neighboring cations is equal to the charge on the anion. So, and that you know, we have written here on the board, we have written all this, or I have written them, but you put in this then in your notebook. We have to do this electron charge balance, yeah, between the anions and the cations, yeah. The other ones are negative, the other ones are positive. Rule number 3, the existence of edges and particular phases common to two anion polyhedra in a coordinated structure decreases its stability. Yes, you know this by now. Also a good example, that is the biotype or the K-feldspar when you are removing the potassium. Yeah, there is only one electron in the outermost ring, so when this potassium can remove very easily. Yeah? So whereas if you have other cations with a higher electron charge, then or with more electrons in the outermost ring, then they cannot remove so easily. So this effect is large for cations with high valency and small coordination number. So and that is then also illustrated in the graphic. So and then you can go page down. Rule number 4, in a crystal containing different cations, those of high valency and small coordination number tend not to share polyhedral elements with each other. And the rule number 5, the number of essentially different kinds of constituents in a crystal tends to be small, because characteristically there are only a few types of contrasting cations and anion sites. But now let us go to the illustration. So here we have again the coordination numbers, yeah? So here we have in the middle then one cation surrounded by 3 anions, then we have a coordination number of 3. Then here we have 4, one cation in the middle, 3 anions surrounding. Then we have here coordination number of 6, one cation in the middle surrounded by 6 anions. And here we have a coordination number of 8. We have one cation in the middle surrounded by 8 numbers. So, and that is then rule number 1, yeah, which is written here. And here you have the author have given again the explanation. Then we are going to rule number 2. So here we have to select one of the polyhedras. Then we just selecting this one. So, and that is the electrostatic valency principle. That means here we have a cation with a charge of +1, and then it has to be shared by 6 atoms here. Yeah? Here we have a sodium in the middle. Sodium has 1 electron in the outermost rim, and here we have the chlorine at the rim. So, and then it is always divided by 6. Yeah? So, and I mean, therefore you are connecting this octahedral with another one. So, and or every of this chlorine is then connected to other 5, including this one. Then we have 6. Or all in all, these are then 6 octahedrals, and always in the middle is 1 sodium. Yeah, because 1 chlorine has 1 negative, is 1 times negative charge. So, and therefore you have to connect every chlorine with another 6 sodium. So, and then you are forming this package. So we can just run the movie. There is not that much seen in the movie. But anyway, I think you got it now, yeah? I showed you this in class with the silica tetrahedron that you have in the middle, the silica which has 4 electrons in the outermost rim. So, and then you have 4 oxygen in the outermost rim. So, and these 4 oxygen are always sharing with other tetrahedrons to complete the charge balance. Let us just select this one. So, here for example we have the calcium fluoride. Calcium has 2 electrons in the outermost rim, so and then we have here always divided by 4. That means 0.25. And if we are multiplying 2.5 with 8, yeah, then we are getting again 2, and then the balance is finished. But then there are some, here is always 0.7 left, yeah. So, and that has then connected with other 3 cubic cells. So, but here you have again the description. So then we are going previous, then we are going to this one. So, and this one is a very famous one. Yes, there we know it's not that famous. I thought it is now the silica tetrahedron. Here we have also, we have calcium fluoride. Here we have fluorine in the middle, it is -1. And here the calcium outside. And then we have is sharing always 0.25 with the fluorine in the middle. Yes. Rule number 3. So rule number 3, here we have now 2 octahedrons connected to each other, and here we have 2 tetrahedrons connected to each other. Starting with the octahedrons. So again, the red bubble is the cation, the blue bubble is the anion, and then here is then just the radius. So, and now we can see what happens here. So then this, if we are increasing the pressure, yeah, for example, then our tetrahedrons can then just be connected in another way, yeah. For example, if you are watching it again, then we have here a radius of 1. Now we are going to a radius of 0.71. Now you are going on a radius of 0.58, yeah? So, and therefore, with changing temperature and pressure condition, you are always changing the symmetry, yeah? Without changing the mineral chemistry, yeah? Because the mineral chemistry, you know this by now as well, you can also change, or it will also change while you are changing pressure and temperature conditions or fluid activity, but mainly it is pressure and temperature. So now we have here 2 tetrahedral sharing, yeah? We have here again cation and anion, we have here a radius of 1, and now we are starting the movie. So now we are going to 0.58, and now we are going even much closer to 0.33. Rule number 4. So here we have a tetrahedron, and here we have as well. What happens here? Here we have a crystal which contains different cations, those of high valency and small coordination number tend not to share. So then we are just moving 2 of the tetrahedrons together. So that means they are sharing not the edge, they are only sharing the edges, yeah? And that is the edges of the tetrahedron, but the cations will not share because here we have just two different cations. Rule number 5, and this one you know by now, that is just our clino-amphibole structure. Yeah, we have here again, we have here our A side, that is the interlayer. We have M4 spaces, M1, M2, M3 spaces, and we have the tetrahedrons. Yeah, I showed you this also before. So, and here we have all our here we have the tetrahedrons, and here we have different octahedrons, and these are in different colors. So, and that means that we have here, for example, in the amphiboles, we have different octaeder spaces, and I mean on the bigger octaeder spaces, there we have bigger atoms, and on smaller octaeder spaces, we have smaller atoms, and on the tetraeder space, we have even much more smaller atoms. And certain atoms are always located to certain spaces, and that is because of the size. So now we have a perspective view, that is how it looks like along the 1, 0, 0, 1 axis. I will give you later more details about it. Then we have the down A-axis view. So that is just from another perspective, yeah, because you have 3 axes. So then we have here the A-axis, we have the C-axis, and here we have the B-axis, and that is how it looks like from the A-axis view, that is from this side, yeah? So, but if we are checking the picture from before, but we must not check it again, that is then just from above, and that is the bird's view, yeah? Yes, the bird is always looking from top to the bottom, yeah? At least those which I know. So, and then we have the down B-axis view, and that looks then so, yeah? So, and there you have then the different arrangement of your cations, and here, for example, here is again the description. On the A side we have the largest cations, yeah, that is sodium and potassium, or it can be vacant, I showed you this, when we have drawn it to the board. Then we have on the N4 side, we can have sodium, calcium, manganese, iron 2+, Mg2+. On the M2, M1, M2 and M3 we have then iron, magnesium, but we can have then also the smaller ones like iron 3+, aluminium 3+, or titanium. And the tetrahedral side we have silica, or we can replace it with aluminium 3+. So yeah, but you should know this by now. So, but the CD is very good for learning, yeah, and therefore I'm suggesting that you should also go through all this stuff. So then we have architecture of layer silicates. We have done this as well, but here you have then again some movies. And this machine is now 13 years old, and one can feel this every time on the speed. Simply just restarting it. Now something happened. Yeah, good, then we are done for today. I will upload then all the stuff what we have done by now on Moodle, yeah.